In this video, we'll talk about the derivative and how we define it. When we talked about the tangent problem, we saw that the graph of y equals f at x has a tangent line at a point a comma f at a having slope m given by a limit. The limit as h approaches 0 of f at a plus h minus f at a divided by h, provided this limit exists. If we look at the picture, we see that we have a curve here, y equals f at x. The blue line is a secant line. The secant line passes through the points a comma f at a and a plus h comma f at a plus h. The secant line passes through the curve in two places. We imagine that this number h is very small, and in fact, as h gets smaller and smaller, the distance between these 2 points gets smaller and smaller. Imagine taking this blue point and moving it along the curve so that it gets closer and closer to the other point. That's really what we're doing when we compute this limit. This quantity right here, f at a plus h minus f at a divided by h, this is the slope of the secant line. This is the slope of the blue line for any given h. This is the difference of the y values divided by the difference of the x values. You can see that the x values are a and a plus h. So if we take a plus h and subtract a from it, we just get h. In the limit, we get the tangent line. And so the slope of the tangent line is the limit as h goes to 0 of the slopes of the secant lines. When we look at velocity, we encountered a similar picture. If f at t is the position of an object relative to a fixed point after t seconds or t units of time, then the instantaneous velocity at time t equals a is given by a similar object. V, for the instantaneous velocity, is the limit as h goes to 0 of f at a plus h minus f at a divided by h. In this case, the blue line, well, it's a secant line again, but this quantity, f at a plus h minus f at a over h, represents a physical quantity. And in that case, it's the average velocity over time, starting at a, time a, and going to time a plus h. The average velocity over this time interval turns out to be equal to the slope of the secant line that passes through these 2 points. And if we compute the limit of this slope as h goes to 0, we end up with the slope of a tangent line. The slope of this tangent line is the instantaneous velocity. Again, provided this limit exists. When defining the slope of the tangent line and the instantaneous velocity, we computed the limit of a certain quantity. This was the difference of the y's over the difference of the x's. We call this quantity a difference quotient because it's a quotient of differences, the difference of the y values divided by the difference of the x values. And when we computed the slope of the tangent line and the instantaneous velocity, we looked at a limit of these difference quotients as the denominator went to 0, as h went to 0. In the case of the tangent line, the difference quotient represents the slope of the secant line that passes through the 2 given points. In the case of the velocity, the difference quotient gives the average velocity over the given time interval. Perhaps the miraculous thing is that these are actually the same. Finding the slope of a tangent line using the slope of secant lines turns out to be the same problem as finding the instantaneous velocity using the average velocities. In order to obtain the slope of the tangent line, or the instantaneous velocity, we compute the limit of a difference quotient as h goes to 0. This limiting value has a name, and we call it the derivative. Let's write this as a definition. if f is a function and a is a point in the domain of f, then the symbol f prime of a is given by the limit that you see here. F prime of a is equal to the limit as h goes to 0 of this difference quotient. F at a plus h minus f at a divided by h. This difference quotient is the same as the difference quotient we've been looking at. This is the slope of the secant line, or the average velocity. We compute the limit as h goes to 0 of this quantity, and if that limit exists, we call that value of that limit f prime of a. This is the derivative. If the limit exists, f is said to be differentiable at a, and f prime of a is called the derivative of f at a. Notice that if you simply plug in h equals 0, you'll end up with 0 over 0. If you just try substitution, if you plug in h equals 0, you end up with a 0 in the denominator, but you also end up with a 0 in the numerator, because if h goes away, you just simply have f at a minus f at a. 0 over 0 is what we call an indeterminate form. It might have a value, but we might have to do something to determine that value. The tangent line to y equals f at x at a given point, a comma f at a, has slope f prime of a. That's something we've already seen. So as an example, if y equals f at x is the graph of the function f at x equals x squared minus 4x plus 5, so in other words, it has this parabola as its graph, then the tangent line at 3, 2 has equation y equals 2x minus 4. The slope of this tangent line at this point, 3, 2, is 2. That means that the derivative at this point is 2. In this case, the difference quotient represents the slope of a secant line for a curve that passes through the points a, f at a, and a plus h, f at a plus h. And as you compute the limit of this difference quotient as h goes to 0, the slopes of these secant lines approach the slope of the tangent line, which in this case is 2. If f at t is the position of an object relative to a fixed point after t seconds or t units of time, then the instantaneous velocity at time a is f prime of a. If an object is propelled upwards from the surface of the Earth with a velocity of 10 meters per second squared, the height above ground level after t seconds is given by this formula. F at t is equal to minus 1/2 g times t squared plus 10 times t, where g is the acceleration due to gravity. We put a minus sign in front of it just to indicate that it's going downwards. After 1.5 seconds, the velocity is approximately minus 4.7. In this case, the units are meters per second. The difference quotient in this case gives the average velocity over a time interval. And if you compute the limit of those average velocities as h goes to 0, you end up with the instantaneous velocity, which in this case is minus 4.7. That's also the slope of this blue line. This blue line is the tangent line to the curve. Notice that it's negative. That's because the slope is negative. But that means that the object that's traveling is returning to the fixed point. It started off by going away and then coming back. In this particular case, the fixed point is the starting point on the Earth's surface. The object is propelled upwards. It goes up, and then eventually gravity pulls it down. That's why the velocity is negative at time t equals 1.5, because at that time the object is returning to the Earth. So the velocity is negative to indicate that it's returning to the fixed point. Let's start out by computing some simple examples. For our first example, let's look at f of x equals x squared and compute f prime of 3, that is, the derivative at 3. So we start by writing down the limit definition. F prime of 3 is equal to the limit as h goes to 0 of f at 3 plus h minus f at 3 divided by h. So that's the limit as h goes to 0 of the difference quotient. So this is the limit as h goes to 0, and now we need to compute these things. Well, our function f at x takes the input, and whatever this input x is, it squares it. It's the square function. So our first input is 3 plus h. So we take the 3 plus h and square it. 3 plus h, that's our input, and then we square it. Minus f at 3, that's just the square of 3, which is 9, divided by h. The next step is to multiply out this 3 plus h quantity squared. So we have the limit as h goes to 0 of 3 squared is 9 plus 2 times 3 times h plus h squared. And from this we subtract 9. We can put this in parentheses if we want. Now we notice that there's a 9, subtract a 9. So those will cancel. And we'll have the limit as h goes to 0 of 6h plus h squared divided by h. Notice that there is an h in every term here, so we can factor out an h. We'll have the limit as h goes to 0. We factor out an h in the numerator, 6 plus h divided by h. So now we have a factor of h in the numerator and a factor of h in the denominator. We can reduce this expression, and we'll have the limit as h goes to 0 of 6 plus h. What we're left with is a polynomial, 6 plus h. It's a polynomial in h, so we can simply use the substitution rule to compute this limit. Another way of saying that is that 6 plus h is continuous with respect to h. So we just plug in h equals 0, and we get 6. Therefore, the derivative f prime of 3 is equal to 6. That means the slope of the tangent line to y equals x squared when x is equal to 3 is 6. Let's do another example. If g of x is 1 over x, then compute g prime of 2, that is, the derivative at 2. So again, we just write down the derivative using its definition. The limit as h goes to 0 of g at 2 plus h minus g at 2 divided by h. Again, at this point, we just simply use the definition of our function. In this case, g of x is equal to 1 over x. So you take the input, and the output is just 1 over that input. In this case, our first input is 2 plus h. So this is going to be equal to the limit as h goes to 0. So g at 2 plus h is 1 over the input minus g at 2, which is 1 over 2. And all of this divided by h. Now you might wonder at this point if you can just simply plug in h equals 0, and you can't, because you end up with an h in the denominator that goes to 0, and there's also an h here. So if you just plug in h equals 0 here in the numerator, you'll have 1/2 minus 1/2, so you end up with 0 over 0. This is normal. When you're computing the derivative using this limit definition, you'll always end up with a 0 over 0. You have to simplify the expression somehow so that you can get an h in the numerator to cancel out with the denominator. Notice that we did that in the last example. So if we go backwards, we started off with a 3 plus h quantity squared minus 9 over h. And again, if you just simply plug in h equals 0, the h goes away in the numerator and you have 3 squared, which is 9, minus 9, which is 0, divided by 0, so you have 0 over 0. But if you have a 0 in the numerator, when h goes to 0, that means that somewhere buried in there, there's a factor of h. You just have to figure out where it is. You figure out where the factor of h is, factor it out, and then it cancels with the h in the denominator. And then you can just substitute in h equals 0. So let's go back to our next example here, the example we're working on. So there's a factor of h in the denominator, but if you just plug in h equals 0, the numerator goes to 0 as well. So somewhere buried in here there's a factor of h. We have to figure out where it is. And the way to do that is to combine these terms. First, give them a like denominator. So this is the limit as h goes to 0. So we're going to give them a common denominator. So we have 1 over 2 plus h. We need to write this as 2 over 2. Then minus 1/2 times 2 plus h over 2 plus h. And all of this is divided by h. So we had a 2 plus h here, and we had a 2 here. 2 plus h and 2. So here's the 2 plus h, there's the 2 plus h. And then we had a 2 here and a 2 here. So we want to give these a common denominator. So this one has a 2 plus h but needs a 2. So you multiply by 2 over 2. This term has a 2 in the denominator, but we need a 2 plus h. So you multiply by 2 plus h over 2 plus h. Okay, now we simplify. So this will be the limit as h goes to 0. That's supposed to be an h, goes to 0. So it'll be 2 over 2 plus h times 2 minus 2 plus h over 2 times 2 plus h. Everything here divided by h. Now the two terms in the numerator can be combined into one because they have a common denominator. So it's the limit as h goes to 0 of 2 minus 2 plus h. All of that's divided by 2 times 2 plus h. And this is the numerator here. That's the numerator, divided by h. Let me just fix that. Divided by h. So all of this is combined into this term right here. But notice that we have a 2 here, and we're subtracting a 2 there. Let's just write it all out. So this is the limit as h goes to 0. And again, we're just looking at the numerator now in this bracket. So it's going to be 2 minus h divided by 2 times 2 plus h. And everything here is divided by h. 2 minus this quantity 2 plus h. So you subtract the 2 and subtract the h. And now we have a 2 minus 2. So this 2 cancels with that 2. And what do we have? We have the limit as h goes to 0 of minus h divided by 2 times 2 plus h. And this quantity is divided by h. So dividing by h, so dividing by this h is the same as multiplying by its reciprocal. So this is minus h over 2 times 2 plus h. And I'm going to multiply this by 1 over h. So this h is the same as that h. Dividing by h is the same as multiplying by 1 over h. And now this h cancels, that h can cancel with that h, and we'll be left with the limit as h goes to 0 of minus 1 over 2 times 2 plus h. At this point, we have a function which is continuous at h equals 0. That is to say, you can just plug in h equals 0. This is a rational function. This is a rational function, so you can just use the substitution rule, provided you're not dividing by 0. H is going to 0, but we don't have a factor of h in the denominator. We have a factor of 2 plus h, and that doesn't go to 0, that goes to 2. So this limit is now minus 1 over 2 times 2 plus 0, so it's minus 1 over 4. And that's our answer. That is to say that the thing that we were trying to compute, g prime of 2, is equal to minus 1/4. Let's just write that somewhere. G prime of 2 is equal to minus 1 over 4. Let's do another example. Here we have a function k at x equals the square root of x, and we want to compute the derivative at 4. So again, we're going to use our limit definition. So k prime at 4 is equal to the limit as h goes to 0 of k at 4 plus h minus k at 4. And all of this is divided by h. Okay, well, k is the square root function, so whatever the input is, you just compute the square root of it. So we're going to have the limit as h goes to 0 of the square root of 4 plus h minus the square root of 4, which of course is just 2, divided by h. Once again, if you simply substitute in h equals 0, you're going to have the square root of 4 minus the square root of 4, which is 0, divided by 0. 0 over 0 is indeterminate. That means the limit might exist, but you can't just plug in h equals 0 to figure out what it is. So what are we going to do in order to determine the value of this limit? Well, when you plug in h equals 0, you get a 0 in the denominator, but you also get 1 in the numerator. And that means that there's some factor of h buried in here somewhere, and you just have to bring it out somehow. And the way that we're going to do that is by getting rid of these radicals. So we're going to multiply by the square root of 4 plus h plus the square root of 4, divided by, if you multiply it in the numerator, you have to multiply it in the denominator as well. The whole reason you want to do this is you're setting up a difference of squares in the numerator. So you have an a minus b, and we want to multiply that by a plus b. And the result will be a squared minus b squared. So in other words, you're going to end up getting rid of all of these radicals in the numerator. You'll pick up some radicals in the denominator, but that's fine because h is going to 0, and in the denominator, this term that you're adding in does not go to 0, so you're not adding in any problem areas. So let's just go ahead and do this multiplication. So this is the limit as h goes to 0. In the numerator, we end up with the square root of 4 plus h, quantity squared, minus the square root of 4, quantity squared. And all of this is divided by everything in the denominator, h times the square root of 4 plus h plus the square root of 4, which we might as well just call 2. Okay, let me just move this down just a little bit. Okay, so now this is the limit as h goes to 0, and we compute the square root of a radical, so the radical goes away, so we have 4 plus h minus the square root of 4 squared, so that's 2 squared is 4. And we divide this by, and you don't do anything to the denominator, you just leave it as it is. So it's h times the square root of 4 plus h plus 2. And we have this 4 cancels with that 4, and we end up with the limit as h goes to 0, and in the numerator we have an h divided by h times the square root of 4 plus h plus 2. Now we have an h in the numerator and an h in the denominator. These are the culprits that gave us 0 over 0 to begin with. The first h, the h in the denominator, that's been with us all the time. The h in the numerator has been hidden, but we've managed to lure it out. So this is the h that was giving us the 0 in the numerator all along, but now it reduces with the 1 in the denominator. And you just have the limit as h goes to 0 of 1 over the square root of 4 plus h plus 2. Now there is an h in the denominator, but notice that as h goes to 0, you don't end up with the denominator going to 0. This is the square root of 4 plus h. So when h goes to 0, this just becomes the square root of 4. So we end up with 1 over the square root of 4 plus 2. Now the square root of 4 is 2. So this is 1 over 2 plus 2, which is 1/4. So k prime at 4 is equal to 1 over 4. And that's our answer. Let's look at another example. In this case, we have f at x is equal to mx plus b. That is, f at x is equal to a linear function. That is, the graph is a line. The graph of this function is the line y equals mx plus b, a line that has slope m and y-intercept b. So we want to compute the derivative at an arbitrary point a. So let's do that. F prime of x is equal to the limit as h goes to 0 of f at x plus h minus f, oh, not x, we're doing this at a. So this should be an a, and that should be an a. Minus f at a. There we go. Divided by h. Okay, so this is the limit as h goes to 0. And how do we compute f at a plus h? Well, whatever is the input, so our function f at x gives us mx plus b. So whatever the input is, we take that input, multiply it by m, and then add b to it. So we're just going to replace this x with a plus h. So this is going to be m times a plus h plus b. And from this, we're going to subtract, so that's the first one. And from this, we're going to subtract f at a. So that's just f at a, you just take the x and replace it with a. So it's just going to be m times a plus b. Notice my use of brackets here. I don't want to lose any minus signs. So this f at a plus h is this term right here. And this f at a is this term right there. So this is going to be the limit as h goes to 0. So let's just expand all of this. M times a plus h, that's going to give us an ma plus mh plus b minus ma minus b over h. That's supposed to be an h. Okay, now this ma cancels with that ma. And this b cancels with that b, and you're just left with the limit as h goes to 0 of mh in the numerator divided by h in the denominator. And those h's will cancel, and you're left with the limit as h goes to 0 of m. Well, m is a constant. M is the slope of this line. So the limit as h approaches 0 of m is just m. So f prime of a is equal to m. So in other words, if you start with a linear function, then the derivative at any arbitrary number a is just going to give you the slope of the line. This is believable because we know that the derivative at a gives you the slope of the tangent line at a. But here we're looking at a graph which is a line. So instead of giving you the slope of the tangent line, it's giving you the slope of the line you started with. So if we start with graphing, if we have the graph of some, let's change the color here. So if we have the graph of some function which is linear, so this is y equals mx plus b, then that means that the slope of this line is m. And what that tells us is that if you compute the slope of the tangent line at any point, it's also m. So if you start with a line, the tangent line is just the line again. So the tangent line for a line is just the same line. So the derivative of a linear function is going to just give you the slope of that line back. Let's look at another example. Here we have the absolute value function. If g at x is equal to x, then compute g prime at 2 and g prime at negative 2. So let's start with g prime of 2. So this is going to be equal to the limit as h goes to 0 of g at 2 plus h minus g at 2 divided by h. So this is going to give us the limit as h goes to 0 of the absolute value of 2 plus h minus the absolute value of 2 divided by h. So the absolute value function just gives you the argument back if the argument is positive. So here we have the absolute value of 2, that's just going to be 2. What about this 2 plus h? Well, h is close to 0, so 2 plus h is really close to 2, so it must be positive as well. So we're just going to end up with the limit as h goes to 0 of 2 plus h minus 2 over h. So this 2 will cancel with that 2, and you just have h over h. So this is the limit as h goes to 0 of h over h. Notice that this is a 0 over 0, but it reduces immediately. This is the limit as h goes to 0 of 1. Well, again, 1 is constant, so it doesn't care what h is doing, so this is just going to be equal to 1. So g prime of 2 is equal to 1. Okay, what about g prime at negative 2? G prime at negative 2 is equal to, well, we compute it the same way. The limit as h goes to 0 of g at minus 2 plus h minus g at minus 2 divided by h. So this is equal to the limit as h goes to 0 of the absolute value of minus 2 plus h minus the absolute value of negative 2 over h. Well, now we have a negative number here. So the absolute value of negative 2 is going to give you a positive 2. But what about this? Well, this is also a negative number. H is really small, it's close to 0. So negative 2 plus h is going to be really close to negative 2. So the absolute value is going to give us a positive number. So it's negative right now, so this is going to be the limit as h goes to 0. So it's going to give us the opposite of that. So it's going to be minus negative 2 plus h minus, and again the absolute value of this is 2. So here, this quantity minus 2 plus h in absolute value, since we know that minus 2 plus h is negative, if you compute the absolute value of that, you're going to get the opposite. So that's where that minus sign comes from. Don't think of this minus sign as a minus sign, think of it as the opposite. Since minus 2 plus h is a negative number, the absolute value gives you the opposite of minus 2 plus h. And all of this, of course, is divided by h. Okay, so let's just simplify the numerator. So we have the opposite of negative 2 is positive 2, minus h, minus 2, divided by h. And now this 2 cancels with that 2, and you're just left with negative h over h. So the limit as h goes to 0 of negative h over h. And these cancel again, and we're left with negative 1, which just like last time is a constant, so it's just minus 1. Consequently, g prime of negative 2 is equal to negative 1. So g prime at 2 is positive 1, and g prime at negative 2 is negative 1. If you think about what the graph of this is, that shouldn't be a surprise. Let's just go to the next slide where there's a graph. This is the graph of the absolute value function. And you can see that if x is positive, then you just have the graph y equals x. And the slope of that is 1. That's a line. It's a straight line. As long as you're looking for x positive, then your graph is a straight line having slope 1. And we saw in our previous example that if you have the graph of a line, then the slope of the tangent line is just the slope of the line. So the derivative is the slope of the line. So that means that the derivative is going to be 1 there. If x is negative, then y is equal to negative x is the graph. So now you have, again, a linear function, g at x equals negative x, and this is a straight line, this graph, with slope negative 1. So that means the derivative is going to be negative 1. So we write that as a piecewise defined function. G prime of x is equal to 1 when x is greater than 0, and negative 1 when x is less than 0. And remember, the absolute value function was really piecewise defined as well. G at x equals the absolute value of x is equal to, well, it's equal to x when x is positive, and it's equal to the opposite of x when x is negative. Now, the thing about the absolute value of x is it's also defined at 0. So we can pick either one of these, because either one of these is going to give you 0. So the absolute value of 0 is 0, so you can either use the top rule or the bottom rule. So let's just arbitrarily use the top one. Well, what about our derivative, g prime of x? We have a rule here for when x is positive and a rule when x is negative. But what about when x is equal to 0? Is it going to be one of these? Can we do what we did before? For the definition of the absolute value of x, we wrote it as a piecewise defined function, and we were able to include the case x equals 0 in either one of these. Well, it can't be quite that simple here because when x is positive you have 1, and when x is negative you have minus 1, so those won't be the same at 0. So the question is, what do you do about 0? How do we assign a value to that? Well, let's try to compute it. So here's our next example. If g at x is the absolute value of x, is it possible to compute g prime of 0? So let's find out. G prime of 0, if it exists, is the limit as h goes to 0 of g at 0 plus h minus g at 0 divided by h. Okay, well, this is the absolute value function. G is the absolute value function, so this is the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 divided by h. Okay, well, the absolute value of 0 plus h, well, let's write this down. The limit as h goes to 0, this is the absolute value of h. And of course, the absolute value of 0 is just 0. So we're just going to end up with the absolute value of h in the numerator divided by h. The limit as h approaches 0 of the absolute value of h over h. But this limit does not exist. And why is that? We've actually seen this before. If you look at the graph of y equals the absolute value of h over h, what's that going to look like? Let's draw it in. Well, if h is positive, so this is the horizontal axis is the h-axis here. So if h is positive, if h is greater than 0, then you have the absolute value of h over h is equal to h over h is 1. So if h is positive, then all of your values are 1. However, if h is negative, then the absolute value of h over h is going to be the opposite of h over h, which is minus 1. So that means all of your values are down here, like this, at minus 1. Now, what about h equals 0? Well, h never actually equals 0. We're looking at the limit as h gets closer and closer to 0. This quantity doesn't exist when h is equal to 0. The question is, what is the limit as h gets close to 0? So you have a little hole here on both of these pieces. As h approaches from the right, you get 1. As h approaches from the left, you get -1. Well, that means that the right limit doesn't equal the left limit, so the limit doesn't exist. So this limit doesn't exist. That means that g prime of 0 doesn't exist. So this function is not differentiable at 0. So this function is not differentiable at 0. So not all functions can be differentiated at every point. Let's look at another example. If f at x equals x times sine of 1 over x, does f prime of 0 exist? Well, let's try to compute it and see what happens. F prime of 0 is equal to the limit as h goes to 0 of f at 0 plus h minus f at 0 divided by h. It's supposed to be an h. Well, immediately we have a problem because f of 0 doesn't exist. F of 0 is not defined. 0 is not in the domain of this function. You might remember way back when we first defined the derivative was defined at a point a in the domain of the function. 0 isn't even in the domain of this function, so it's a non-starter. We can't even begin because we can't compute that. In fact, it's not enough for a function to be defined, it has to actually be continuous. And there's a theorem to that effect. In order for a function to be differentiable at a, it is necessary for the function to be continuous at a. And we can see that from the definition. The definition of the derivative is in terms of a limit. So f prime of a is the limit as h goes to 0 of this difference quotient, f at a plus h minus f at a over h. Well, the denominator is just an h, which is going to 0. So the denominator is going to 0. So the only way that this limit could possibly exist is if the numerator is going to 0 as well. If the numerator was just going to some non-zero value, then this would be an infinite limit of some kind. But that's not the case if this function is differentiable. If the function is differentiable, then this limit needs to exist. And the only way that can happen, since the denominator is going to 0, is if the numerator goes to 0 as well. But if the numerator is going to 0, that means that f at a plus h is going to f at a. And that just means that f is continuous at a. The theorem says that in order for a function to be differentiable, it must be continuous. But you need to be careful about that. A function can be continuous at a, but not differentiable there. We just saw that the absolute value function is not differentiable at x equals 0, but it is continuous there. This function, g at x equals the absolute value of x, this function is continuous everywhere. If we go back to the graph, which is back here somewhere, this graph is the graph of a continuous function. There are no holes, there are no jumps. What there is a point. That point is what gave us the problem. This function is continuous because the pieces of this curve connect. It's defined everywhere. There are no holes, there are no jumps, and there are no gaps. But because of this corner point, there was no derivative. Okay, so g at x equals the absolute value of x is an example of a function which is continuous at 0, but not differentiable at 0. But what about our function here, f at x equals x times sine of 1 over x? Now this function wasn't even defined at 0, but maybe we can define it there. Maybe we can redefine this function. In fact, it turns out that this function has a removable discontinuity at x equals 0. Can we figure out what it is? Is there some value we can assign to f at 0 so that the function is continuous at 0? Now here's a graph from x equals -1 to 1, and you can see that there's a lot of oscillation happening, but it does sort of seem like the function is narrowing down towards the origin. It looks like it's narrowing in on that point. Well, let's zoom in and get a better look. Zooming in makes it convincing that the values do tend towards 0. There's a lot of oscillating, but it seems to be narrowing in on 0. Well, it seems to be. Can we prove it? And yes, we can. We can, in fact, show that x times sine of 1 over x goes to 0 as x goes to 0 using the squeeze theorem. So here's the same graph. This is the same graph as before, but now we've just added 2 lines to it. This blue line is the line y equals x. So this is y equals x. And the red line is y equals negative x. And the graph in the middle, of course, is y equals x times sine of 1 over x. And what you'll notice here is that the graph in the middle is always between these two curves. Now, when you pass through 0, y equals x and y equals negative x intersect. So the function which is on top for negative values swaps with the other function. So when x is negative, y equals negative x is on top. But then when you pass through 0, y equals positive x is on top. But when x is negative, y equals positive x, well, not positive x, y equals x is on the bottom, and then y equals negative x is on the bottom after you pass through x equals 0. But either way, you can see that the function we're interested in, x times sine of 1 over x, is sandwiched in or squeezed in between these two curves. And in fact, we have these inequalities. When x is less than 0, we have that x is less than or equal to x times sine of 1 over x is less than or equal to negative x. And when x is positive, we have that negative x is less than or equal to x times sine of 1 over x is less than or equal to x. Now, why is this true? That's simply true because sine of anything is between -1 and 1. So we know that sine of anything is always between 1 and -1. So if you multiply it by x, then you either end up with this set of inequalities if x is positive, or this one if x is negative. It's the same thing, but x is negative, so you have to change the direction of the inequalities. Either way, you have x times sine of 1 over x squeezed between two terms which are going to 0. And as a result, the thing in the middle has to go to 0 as well, by the squeeze theorem. So anyway, we can redefine the function f as follows. F at x is equal to x times sine of 1 over x when x is not equal to 0, and 0 when x is equal to 0. Redefining the function in this way removes the discontinuity, so this function is continuous at x equals 0. But is it differentiable at x equals 0? Well, we can compute it directly to find out. F prime at 0 is equal to the limit as h goes to 0 of a difference quotient. That's f at 0 plus h minus f at 0 over h. So what is this equal to? Well, f at 0 plus h is just f at h, and f of 0 is f of 0. So f at h is h times sine of 1 over h. So here I'm just taking these x's and I'm replacing them with h, because this is f at h. So just take that x and replace all of the x's with h's. So it's h times sine of 1 over h. And here we're subtracting f of 0. Well, what is f of 0? It's 0. So it's minus 0. So we have the limit as h goes to 0 of h times sine of 1 over h divided by h. And we have an h here and an h here, so this reduces, So this is the limit as h goes to 0 of sine of 1 over h. However, this limit does not exist. Does not exist. How do we know that? Well, this has an oscillatory discontinuity at h equals 0. If we look at the graph, we can see it. This is the graph of y equals sine of 1 over h. So h is the horizontal axis here. And as h goes towards 0 from either side, you see that sine of 1 over h oscillates wildly. And in fact, this limit doesn't exist because the y values here don't approach one value as h goes to 0. Y approaches infinitely many values, every value between -1 and 1. So that limit doesn't exist. If this limit doesn't exist, then that means the limit of the difference quotient doesn't exist, and that means the function is not differentiable at x equals 0.